Okay, so once again, welcome back to another topic. So for today is we will be discussing all about fluid mechanics. So for fluid mechanics, we have these topics that we will be discussing. But for this video, we will be discussing first the mass, density, and specific gravity. The second one is the pressure in a fluid, and the third one will be all about buoyancy. So the fluid flow, Bernoulli's equation, and viscosity and turbulence will be discussed on the next lecture video discussion. Okay, so let's proceed with density. So what is density? So density is an important property of any material. So when we define density, it is defined as the mass per unit volume. So we have the equation for density. We have here this variable right here is what we call the rho. So this is named as rho. So this is the variable for used for density. So rho is equal to m is for the mass divided by capital letter V is for the volume. So we have here in figure 12.1 two objects with different masses and different volumes but the same density. Now, nga naman, because the steel wrench and the steel nail, they are both steel. So, they are both made of steel, so they have the same density, even if they have different masses. So, as you can see, the steel wrench has a greater mass than the nail, but since they are both made of steel, so they have the same density or mass per unit volume. So again, the formula for density is we have rho is equal to mass divided by the volume. Okay, so we have here in table 12.1 some of the examples of the densities of some common substances. So we have here, we have air, ethanol, benzene, ice, water, seawater. We also have blood, glycerine, concrete, and aluminum. So these are some of the substances that has with their densities. So we also have iron or steel, we have brass, copper, silver, lead, mercury, gold, platinum. We have also the white dwarf star and the neutron star. So as you can see, each of this material has a different density. So as notice here that the unit used for density is equal to kilogram per cubic meter. Okay, so kilogram per cubic meter ang unit ni density. So, we also have the conversion from gram per cubic centimeter to kilogram per cubic meter. But again, the SI unit or the basic unit for density is kilogram per cubic meter. But if the given values for density is in terms of grams per cubic centimeter, we can convert that to kilogram per cubic meter. So we have here 1 gram per cubic centimeter is equivalent to 1,000 kilogram per cubic centimeter. So again, for density, the unit or the basic unit for density is kilogram per cubic meter. Okay. So how about for the specific gravity? What is specific gravity? So specific gravity, it is the ratio of its density to the density of water. So ratio of the density of any object or any material to the density of water at 4 degrees Celsius, which is 1,000 kilogram per cubic meter. So again, the density of water is equal to 1,000 kilogram per cubic meter. So divided by the so specific gravity is equal to the density of any material. Let's say density of steel or aluminum or air or any material that is used is you divide that with the density of water, which is equal to 1,000 kilogram per cubic meter, and that will be the specific gravity. So again, specific gravity is the ratio of its density, or the density of the material, to the density of water. Now, how about for the unit of specific gravity? Okay, so since, di ba, we have the ratio of the density of any material divided by the density of water, so the unit, di ba, unit of density is kilogram per cubic meter. So for the specific gravity, the unit will be kilogram per cubic meter divided by, again, still kilogram per cubic meter. So canceled out. So there will be no unit. So purely number lang, or purely value lang ang kay specific gravity. So there will be no unit. So pure value lang siya. Okay. So let's try solving an example for density. So we have right here, find the mass and the weight. So we need to solve 2, which is the mass and the weight of the air at 20 degrees Celsius in a living room with a 4 meter by 5 meters floor and a ceiling 3 meters high, and also the mass and the weight of an equal volume of water. So first, we need to solve for the mass and weight of the air, and also the mass and weight of the water in the same area of the living room. Okay. So now, di ba, take note na density is equal to mass divided by volume. So let's first have the air. So how can we solve for the mass of the air? So using the equation for density, we have the mass is equal to, so we need to multiply both sides with V, or the volume, so that mass is equal to the density of air times the volume. So this will be our equation to solve for the mass of the air. Okay, but now we don't have any value of the volume. So we need to solve first for the volume of this living room. Okay, so to solve for the volume, we have the living room with a 4 by 5 meters na floor and a ceiling of 3 meters high. So the volume of this living room will be length times width times height, which will be, we have 4 meters times 5 meters times 3 meters. So we have 4 times 5 times 3 is equal to 60. We have cubic meter. So this will be our volume for the living room. Okay, so now we can solve for the mass of the air in a living room. So, by the way, the density of air, as you can see right here, is 1.20 kilogram per cubic meter. Okay, so let's use that one. 1.20 kilograms per cubic meters times the volume, which is 60 cubic meters. So we have 1.20 times 60. So as you can see here, for the unit, the cubic meter and the 1 over cubic meter from the unit of density will be cancelled out. So we are left with kilogram, or kilograms. So 1.20 times 60 is equal to 72. And then we have the unit, kilograms. So the mass of the air in a living room with a volume of 60 cubic meters is equal to 72 kilograms. So we are done with the mass. Now let's proceed to the weight of the air. So to solve for the weight, we will just be using the basic formula for the weight, which is mass times the acceleration due to gravity. So we have now the mass of the air times g, or the acceleration due to gravity. So mass of the air is 72 kilograms times acceleration due to gravity, which is 9.8 meters per second squared. So we have 72 times 9.8 is how much? Let's try. 72 times 9.8 is equal to 705.6. Okay, so now (705.6), and then the unit will be kilogram times meter per second squared, or the unit of weight. Weight is again a type of force. So we have 705.6 newtons. So we can also use kilogram meter per second squared, or we can also use newton. So we have now the mass and the weight of the air. Now let's proceed to the mass. So we are done with, again, mass and weight of the air. Now we proceed to the mass and the weight of water. So let's proceed to water. Okay, so to solve for the mass of the water, again, the same procedure using the equation for density. We have the density of water times the volume. So the density of water is equal to 1,000 kilogram per cubic meters. And then we have, again, the volume is still equal to 60 cubic meters. So 1,000 times 60, so again, cancelled out C1 over cubic meter and the cubic meter. So we are left with kilograms. So 1,000 times 60, we have 6 times 10 to the power of 4 kilograms. So this is the mass of the water in a living room. And then for the weight of the water, again, the same procedure. Mass of the water times acceleration due to gravity. So we have the mass of the water, which is 6 times 10 to the power of positive 4 kilograms, times we have the acceleration due to gravity, which is 9.8 meters per second squared. So we have 6 times 10 to the power of 4 times 9.8 is equal to 5.9 times 10 to the power of positive 9 newtons. Or again, we can also use kilogram times meter per second squared. So again, the mass of the air is 72 kilograms and the weight of the air is 705.6 newtons in a living room, whereas the mass of the water is equal to 6 times 10 to the power of positive 4 kilograms, and the weight of the water is equal to 5.9 times 10 to the power of 5 newtons. Okay, so that is how we would solve for the density or the mass and the weight of the air and water using the formula for the density. So again, density is equal to mass per unit volume, or mass divided by the volume of the object. Okay, so now let's proceed to the pressure in a fluid. So the definition of pressure, kung si density is like this, which is again rho, Now, for the pressure, it is small letter P. Okay, basin maglibog mo sa mga variables. So, pressure is small letter P. So, the pressure, the definition of pressure is, it is the change in the perpendicular force applied divided by the change in area. So, this is the definition of pressure in a formula. But, if the pressure daw is the same at all points of a finite plane surface with area, then the pressure in a fluid will now be just the force or the perpendicular force divided by the area or the cross-sectional area. Okay, so how about the unit of pressure? So for the unit of pressure, it is Pascal. So 1 Pascal or 1 PA is equivalent to 1 Newton per square meters. So again, this is Newton and then we have square meters. So 1 Pascal is equivalent to 1 Newton per square meters. But usually, for the pressure is we will be using atmospheric pressure or the pressure of the Earth's atmosphere, the pressure at the bottom of the sea and of air in which we live. So for the atmospheric pressure, we will be using mostly ATM. So ATM is the atmospheric pressure or atmosphere. 1 ATM or 1 atmosphere is equal to 1.013 times 10 to the power of positive 5 pascals. So this is the equivalent of 1 ATM. So again, 1 ATM is equal to 1.013 times 10 to the power of positive 5 pascals. Also, in terms of bar, millibar, and pound per square inches, we have 1.013 bar is equal to 1,013 millibars. And also, it is equivalent to 14.70 pounds per square inches. But mostly, again, in solving pressure in a fluid, we will be using mostly Pascal or ATM or atmosphere. So atmospheric pressure. Okay. So now we have here another example in calculating the pressure in a fluid. So we have here in a room described in the previous example. So the previous example that was mentioned is katong sa density nga example. In the room described in the previous example, the question here is, what is the total downward force on the floor due to an air pressure of 1 ATM or 1 atmosphere? Okay, so take note na sa previous example, the area of the floor is 4 by 5 meters. So to solve for the area is just equal to the length times the width of the floor. So since it is 4 by 5 or 4 meters by 5 meters, so the area will be 4 meters times 5 meters is equal to 20 square meters. Okay. But ang gipangita sa problem is the total downward force or the downward force. So again, using the formula for pressure, pressure is equal to the perpendicular force divided by the area. Okay. So to solve for the force, multiply both sides with area so that it will be cancelled out. So we have pressure times area is equal to the force. Or let's interchange that one. We have the force or the downward force is equal to the pressure times the area of the floor. Okay, so we have the pressure which is 1 ATM. But instead of ATM, we will be using Pascal. Kaya di ba 1 Pascal is equivalent to 1 Newton per square meter. So we will be using converting 1 ATM to Pascal and then 2 Newton per square meters para it will be easier to cancel out the units. Okay, so take note now 1 ATM is equal to 1.013 times 10 to the power of positive 5 Pascal, which is also equal to 1.013 times 10 to the power of positive 5 newtons per square meters. So this is the equivalent of 1 ATM. Okay, so we will be using this value right here. So the pressure of air is, we have 1.013 times 10 to the power of positive 5 newtons per square meters times the area, which is 20 square meters. So as you can see here, 1 over square meters and the square meters right here will be cancelled out. So we are left with the unit newtons. Okay, so the downward force on the floor due to the air pressure is, we have 1.013 times 10 to the power of positive 5 times 20 is equal to 2 times 10 to the power of positive 6 newtons. So this is the value of the downward force on the floor due to the air pressure, which is equivalent to 1 ATM. So again, don't forget the conversion of ATM to Pascal because it will be mostly used in calculating or the density or the pressure, the pressure in a fluid. So again, the force or the downward force is equal to 2 times 10 to the power of positive 6 newtons. Okay, so that is for in calculating the downward force using the formula of pressure in a fluid. Okay, so now let's proceed to the third topic, which is buoyancy. Now, according to Archimedes' principle, when a body is either completely or partially immersed in a fluid, so the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. Okay, so for the definition of buoyancy, buoyancy is the tendency of a body to float or to rise when it is submerged in a fluid. So as you can see, let's say for example, kung maligo ta sa swimming pool or sa dagat, so there is a tendency sa atong body to float or to rise when we are submerged in water, or let's say sea water or sa swimming pool. So the upward force exerted by the fluid that opposes the weight of a partially or fully immersed object. So gimension sa Archimedes principle na the fluid exerts an upward force. So kinsa man si upward force? So this upward force is what we call the buoyant force. So si buoyant force again is the upward force that the fluid exerts on an object that is making us float or rise when we are submerged in a fluid. So the formula, or to solve for the buoyant force is, we call it as FB, but also in other books, they call it as capital letter B. So buoyant force is equal to rho. So again, this one is the density. G is the acceleration due to gravity. And then we have V is the volume. So rho G V. That is the formula for in solving for the buoyant force. Okay. So again, buoyant force, that is the upward force that the fluid exerts on the object or the body. So always remember, buoyant force is equal to the density, or rho GV, or we have the density times the acceleration due to gravity times the volume of the fluid. Okay, so third example, which is for the example of buoyancy, we have right here a 15 kilogram gold statue is raised from the sea bottom. So as you can see here in the figure, that is the situation. So the question here is, what is the tension in the hoisting cable, which is assumed as massless? So si cable is, we assume that as massless, when the statue is, letter A, at rest and completely underwater or completely submerged underwater. And for letter B, we need to calculate still the tension of the cable if the statue is at rest and completely out of the water. Okay, so again, we have for our given values, we have the mass of the statue, which is equal to 15 kilograms. Okay, wait. Okay, so ang gihatag lang nga value is the mass of the statue. And also, we also have, since ang density ni gold is a constant value, we also have the density of gold, which is equal to 19.3 times 10 to the power of positive 3, again, kilogram per cubic meters. Okay, so how can we solve for the tension? So as you can see here, this is the free body diagram of the statue. So the buoyant force, if it is immersed underwater or it is completely underwater, the buoyant force is again the upward force. So this is the location of our buoyant force. And also the tension force is upwards, because again, tension force is the pulling force exerted using a rope or a cord, or in this case, we are using a cable cord. And then we also have the mass, or the weight of the statue, which is equal to mass times gravity. So hatag na diri, which is equal to 147 newtons. Okay. So before we can solve for the tension, is we need to find first the buoyant force. But we cannot still, wala man gihatag si buoyant force. So, di ba, buoyant force, let's have it as B na lang. So, di ba, buoyant force. So, for letter A, okay, wait. For letter A, it is completely underwater. So, it is in sea water. Okay. So, for letter A, we need to find first the buoyant force in sea water. SW is for the sea water. So, di ba, buoyant force is, we have rho, density in sea water, times the acceleration due to gravity, times the volume. So, as you can see right here, we don't have any values of the density of seawater as well as the volume. So we can have the rho of the seawater, but we don't have any volume. So we need to solve first the volume. So how can we solve for the volume of the statue? So we can solve for the volume using the density na equation. So, di ba, take note na density is equal to mass divided by volume. So, to solve for volume is equal to the mass divided by the density. So in this case, to solve for V, this is the mass of the statue divided by the density of gold. So we have V is equal to, mass of the statue is again 15 kilograms divided by, the gold is 19.3 density times 10 to the power of positive 3 kilograms per cubic meters. So again, the unit kilograms in the numerator and denominator will be cancelled out. So we are left with 1 over cubic meters, or it is just equal to cubic meters. So the volume V is equal to, we have 15 divided by 19.3 times 10 to the power of positive 3 is equal to 7.77 times 10 to the power of negative 4 cubic meters. Okay, so we have now our volume. So we can solve for the buoyant force. Okay, so for the buoyant force, we have the density of seawater. So using table 12.1, you can review it later. So the density of seawater is 1.03 times 10 to the power of 3 kilogram per cubic meters times the acceleration due to gravity is 9.8 meters per second squared, and then times the volume, which is 7.77 times 10 to the power of negative 4 cubic meters. Okay. So as for the unit, 1 over cubic meters, and the cubic meters here will be cancelled out. So we are left with kilogram times meter per second squared, or again, it is equal to newtons. Okay, again, diba, buoyant force is still force, an upward force. So the unit will still be in terms of newtons. So 1.03 times 10 to the power of positive 3 times 9.8 times 7.77 times 10 to the power of negative 4 is equal to, we have 7.84. So this is the buoyant force in seawater. 7.84 newtons. Okay. So dili pa na siya maos. Okay. Again, we are solving for the tension. Okay. So as for the tension, balik ta sa ato ang free body diagram. We don't have, as you can see, we don't have any forces. Sum of all forces along the x is equal to 0. But for the sum of all forces along the y is, we have on the positive y, we have the tension plus the buoyant force in seawater minus the weight, which is equal to 0. Okay, so weight is, again, we have now the value of the weight here, which is equal to 147, or 15 times 9.8 meters per second squared. Okay, so we have right here, sum of all forces along the y is equal to the tension plus the buoyant force in seawater minus weight is mass of the statue times acceleration due to gravity is equal to 0. So again, we are asked to solve for the tension. So we will move to the other side of the equation, see buoyant force and the weight. So to solve for the tension, we have tension is equal to weight or mass of the statue times gravity minus the buoyant force in sea water. Okay. So we have mass of statue is 15 kilograms times 9.8 meters per second squared minus the buoyant force, which is 7.84 newtons. So again, kilogram meter per second squared is still equivalent to newtons. So we have 147 newtons minus 7.84 newtons. So the tension, if the statue is at rest and completely underwater or completely submerged underwater, is equal to 100. Let's try to calculate. 147 minus 7.84 is equal to 139.16 newtons. So this is our answer for letter A. So the tension of this cable when the statue is at rest and completely underwater is equal to 139.16. Okay, so that is for letter A. So we still have letter B. Okay, so for letter B, let's continue right here. For letter B, at rest and completely out of water, meaning it is in air na. So wala naman siya sa water. So it is we will be using the density now of air instead of the density of salt water. Okay. So again, to solve for the buoyant force in air, so again, rho of air or the density of air times G times the volume. So the volume is still the same, which is, we will still be using the volume right here, 7.77 times 10 to the power of negative 4. Okay, so for the density of air, then by the way, density of air is equal to 1.2 kilogram per cubic meters. So to solve for the buoyant force, we have 1.2 kilogram per cubic meters times, we have 9.8 meters per second squared, times the volume, which is 7.77 times 10 to the power of negative 4. Unit is in terms of cubic meters. So again, makancel out si 1 over cubic meters and the cubic meters right here. So we are left with kilogram times meter per second squared, or we can have it in terms of newtons. Okay, so we have 1.2 times 9.8 times 7.77 times 10 to the power of negative 4 is equal to 9.1 times 10 to the power of negative 3 newtons. Newton. Okay, so this is now our buoyant force in air. Okay, so the tension okay, so we have for the tension, again, we have sum of all forces along the y is, we have the tension plus the buoyant force in air minus the weight of the statue. It's equal to 0. Okay, so now here to solve for the tension, tension is again equal to mass of the statue times acceleration due to gravity minus the buoyant force in air. Okay, so we have mass of the weight of the statue is 147 newtons minus, we have 9.1 times 10 to the power of negative 3 newtons. Okay, so as you can see, okay, so let's try to calculate. Okay, so we have 147 minus 9.1 times 10 to the power of negative 3 is equal to, the tension now is equal to 146.99, which is, as you can see, since the buoyant force in air is almost negligible compared to the statue's actual weight. So, as you can see, the tension is almost equal to the weight of the statue. So, if we will still convert this into a whole number, so the tension force is just equal to 147. Okay, since it's equal to 146.99, so rounding it off, it will still equal to 147, which is again the weight of the statue. So as you can see, the tension force of the cable when the statue is at rest and completely out of water is equal to 146.99 newtons, or it is almost the same or almost equal to the weight of the statue. Okay, so that is for the buoyancy, or how we would solve for the tension using the equation of the buoyant force. So I think that is it. So for our next discussion, we will be continuing on the fluid flow, the Bernoulli's equation, and also the viscosity and turbulence in our second part of our video. So thank you very much for watching and listening. So we'll see you again on the next video. Thank you.